Elon Musk's new engine may have just ended the EV race. No one saw it coming. Picture a motor small enough to lift with one hand, spinning fast enough to tear itself apart if a single detail were wrong, and powerful enough to launch a 5-seat luxury sedan to 60 miles per hour faster than almost anything else on the road, gas or electric. That motor already exists. It's already on the street. And the strange part is that most people who talk about the electric vehicle race have never really understood why it matters. For years, the story around electric vehicles has been simple. Tesla got there first. Everyone else was catching up. Ford built the Mustang Mach-E and the F-150 Lightning. General Motors rolled out its Ultium platform across nearly every brand it owns. Volkswagen poured tens of billions of euros into its ID lineup. Toyota, the largest automaker on the planet, finally admitted that hybrids and hydrogen weren't going to be the whole answer and started chasing batteries in earnest. The assumption baked into almost every industry forecast was that this gap would close. More competitors, more investment, more factories, and eventually the market would look like every other mature industry, crowded, competitive, with no single company holding a commanding lead. That assumption deserves a second look, and the place to start is with something almost nobody outside of engineering circles pays attention to: the motor itself. Electric motors are not new. The basic idea, using electromagnetic fields to turn electricity into rotation, has been understood for more than a century. What's hard is not the concept. What's hard is the execution, and specifically, one brutal physical trade-off that has shaped every electric motor ever built for a car. The faster a motor spins, the more power it can squeeze out of a given size and weight. That matters enormously in a vehicle, because weight is the enemy of range, of handling, of efficiency, of basically everything an engineer is trying to optimize. A smaller, faster spinning motor beats a bigger, slower one on almost every measure that counts. But spinning something faster creates a problem that has nothing to do with electricity and everything to do with physics. At the center of a modern motor sits a rotor, a spinning core that typically holds powerful permanent magnets. As it spins faster, centrifugal force pulls harder and harder on those magnets, trying to fling them outward. Push the rotational speed high enough, and eventually the rotor simply comes apart. For decades, this was treated as an unavoidable ceiling. Engineers designed around it. They accepted lower speeds in exchange for a rotor that wouldn't destroy itself, and they built the rest of the car around that compromise. Tesla's answer, first shown publicly with the Model S Plaid back in 2021, was to wrap the rotor in a sleeve of carbon fiber, wound under extreme tension using a purpose-built machine the company had to design from scratch, because nothing like it existed. Carbon fiber is remarkably strong for its weight, and wound tightly around the rotor, it acts like a compression band, holding everything in place against forces that would otherwise tear it apart. The engineering problem was harder than it sounds. Carbon fiber and the copper inside the rotor expand and contract at different rates as temperature changes, so the sleeve has to be tensioned precisely enough that the assembly stays locked together in freezing cold and highway heat alike, without cracking or loosening. Tesla built the machinery to solve that problem, and the payoff was a motor that could safely spin in the range of 20,000 revolutions per minute, meaningfully higher than the generation before it, packed into a housing small enough to lift with two hands. The result showed up immediately in the numbers. The Model S Plaid, not a stripped-down test mule, but a full production luxury sedan with air conditioning, a premium stereo, and seating for 5, could hit 60 miles per hour in under 2 seconds and clear the quarter mile in well under 10, figures that put it ahead of cars costing several times as much, including plenty of gasoline supercars, built by companies with decades more experience building fast cars. And it did this while still offering a real-world range in the neighborhood of 350 to 400 miles, depending on configuration. That combination, hypercar acceleration alongside genuinely usable daily range, was supposed to be a contradiction. Performance was supposed to cost you range. Tesla's motor made that trade-off a lot less painful. Here's the part that gets missed in most conversations about this motor, though. The impressive 0 to 60 number is not really the point. The point is, What a design like this signals about how Tesla approaches manufacturing, because a motor that's smaller, simpler, and built around fewer exotic or supply-constrained materials is also a motor that's cheaper to make at scale. Reporting on Tesla's manufacturing strategy over the past few years has pointed to an aggressive, ongoing push to reduce the cost of the entire drive unit, the motor, inverter, and gearbox together, in part by cutting back on rare earth elements, which are expensive, geopolitically sensitive, and heavily concentrated in Chinese supply chains, and in part by reducing dependence on premium materials like silicon carbide in the power electronics. None of this is about chasing a single flashy spec. It's about squeezing cost out of the component that sits at the heart of every electric vehicle Tesla builds. And every dollar saved there is a dollar of margin, a dollar that can become a lower sticker price, a dollar that can fund the next generation of engineering. Compare that to where the rest of the industry stands today. Ford's electric vehicle division has posted billions of dollars in losses in recent years. Money the company has openly acknowledged comes from profits generated by its gasoline-powered trucks and SUVs. That's not a knock on the Mach-E or the Lightning as products. Both have earned respectable reviews. It's a statement about the economics underneath them. General Motors has invested heavily in its Ultium platform, but sales volume has lagged expectations, and the software experience across its EV lineup has drawn persistent criticism. Volkswagen has committed some of the largest sums in the industry to electrification and has struggled with its in-house software division, which has been dogged by delays and leadership turnover, limiting how competitive its ID models have been outside of Europe, where strong government incentives and brand loyalty have propped up demand. The startups tell a different but related story. Lucid builds what might be the most range-efficient electric vehicle on the market today, engineered by a team with deep Tesla roots, and yet the company continues to burn through cash at a low production volume, with a path to sustainable profitability still unclear. Rivian has earned real enthusiasm for its trucks and SUVs, backed by a substantial investment from Amazon, but it has also reported significant losses on every vehicle it delivers. Building a compelling electric vehicle, it turns out, is not the same challenge as building one profitably at scale, and so far Tesla remains the only company in the West that has clearly solved both halves of that problem at once. The one competitor that arguably does rival Tesla on manufacturing scale and cost is BYD, the Chinese automaker that has, in some quarters, sold more electrified vehicles worldwide than Tesla, depending on how plug-in hybrids are counted in the comparison. BYD's dominance, though, sits largely in the budget and mid-range segment, serving cost-conscious buyers in China and expanding developing markets, a different lane from the premium, software-forward vehicles Tesla sells. BYD also faces real headwinds trying to expand into the world's most lucrative markets. Tariffs effectively lock the company out of the United States, and European regulators have opened investigations into subsidies for Chinese-made electric vehicles, creating genuine uncertainty about how far BYD's global ambitions can realistically extend, at least for now. Tesla, meanwhile, has built manufacturing capacity across multiple continents, with major plants in California, Shanghai, Berlin, and Texas, letting it build vehicles closer to the markets that buy them and sidestep some of the tariff and logistics headaches that hem in competitors. Each of those factories represents years of accumulated operational know-how that isn't easy to copy just by writing a bigger check. That's infrastructure in the truest sense: expensive, slow to build, and hard to catch up on quickly. There's another layer to this that has nothing to do with motors or factories at all, and it might end up mattering more than either one. Every Tesla on the road, whether it's being driven to the grocery store or sitting in traffic, is quietly gathering visual data through its cameras and sensors, data that flows back to Tesla and helps train the neural networks behind its driver assistance and autonomy efforts. More cars on the road means more of this data. More data, in theory, means faster progress on the software side. And the software experience is increasingly one of the things car buyers weigh when they choose an EV. Legacy automakers have sold far more cars over the decades than Tesla ever has, but the overwhelming majority of those vehicles were never built to collect or transmit this kind of information, so that decades-long head start in unit sales doesn't translate into a comparable head start in driving data. This is genuinely difficult for a competitor to replicate quickly because it isn't something you can buy off the shelf. It has to be built one fleet, 1 mile, one software update at a time. Batteries tell a similar story of a company trying to control more of its own supply chain rather than rely entirely on outside vendors. Tesla spent years leaning on Panasonic for battery cells, which let it scale up without having to master cell manufacturing from day one. More recently, the company has been developing its own 4680 cell, named for its physical dimensions, aiming for a larger format that simplifies assembly and improves thermal performance. That program has not gone as smoothly or as quickly as Tesla initially hoped. Scaling brand new battery chemistry and manufacturing techniques is notoriously hard, and production ramp has taken longer than early projections suggested. Still, the direction is clear. Tesla wants cells built in its own factories, tuned specifically for its own vehicles, rather than depending indefinitely on suppliers who sell the same cells to every automaker willing to pay for them. That same instinct toward owning more of the stack shows up across Tesla's supply chain, from custom chip designs to in-house infotainment systems. When the global semiconductor shortage disrupted the auto industry in 2021 and 2020, Tesla was able to rewrite software and redesign circuits to work with whatever chips were actually available, while other automakers idled production lines waiting on parts they couldn't get. That kind of flexibility comes from understanding a product deeply enough at every layer to improvise around a shortage instead of being stuck waiting on someone else's fix. Then there's the supercharger network, which might be the clearest example of a long-term bet that looked unnecessary at the time and now looks like one of Tesla's biggest structural advantages. When Tesla started building charging stations back in 2012, spending money on infrastructure looked like a distraction from the core business of building cars. More than a decade later, that network is widely regarded as the most reliable and extensive fast charging system in North America, and it has become such a meaningful part of the ownership experience that competitors have started adopting Tesla's charging connector outright. Ford, General Motors, Rivian, and others have announced that their future vehicles will use Tesla's North American charging standard, meaning their customers will plug into Tesla's own network to charge. That's a remarkable turn of events. Rival automakers effectively depending on infrastructure built and owned by the company they're trying to compete against, generating fees and usage data for Tesla in the process. None of this means Tesla's position is untouchable, and it would be a mistake to treat any single number in this story, whether it's a manufacturing cost estimate or a production timeline, as a settled fact rather than a moving target that changes as the industry evolves. Legacy automakers still have deep balance sheets, established dealer networks, and decades of manufacturing experience that shouldn't be underestimated. Regulatory shifts, changing consumer preferences, and Tesla's own execution risk, especially around ambitious programs like the 4680 battery, could all reshape this picture in ways that are impossible to predict with certainty today. Betting against established industrial giants has been a losing bet before, and it could be again. What does seem fair to say is this: the carbon fiber rotor motor debuted in the Model S Plaid back in 2021. And it was never really the headline on its own. What it represents is a pattern that keeps showing up across nearly everything Tesla builds, a willingness to solve manufacturing problems that other companies considered either too difficult or not worth the trouble, paired with a habit of turning what looks like a cost center, whether that's a charging network, an in-house chip, or a custom battery cell, into a long-term structural advantage. Competing with that pattern isn't just about matching one motor or one battery spec. It means matching the manufacturing discipline, the software stack, the charging infrastructure, the accumulated driving data, and the willingness to spend a decade building things that don't pay off immediately, all at the same time. So far, no single competitor has managed to do that across the board, and the ones making the most progress, like BYD, are working in a different segment of the market entirely. The electric vehicle race that most people imagined, a straightforward contest between car companies building similar products, may simply not be the race that's actually happening anymore. Whether that gap keeps widening or whether the rest of the industry finds a way to close it is still an open question, and it's one worth watching closely over the next few years, because the answer will shape who actually leads the electric vehicle industry a decade from now. VVV